Hey everybody, Dr. A here, and in this video we're going to be exploring a 2D particle equilibrium problem involving a pulley. So let's go ahead and get started.
Asked to determine the mass of cylinder A, given that the mass of cylinder C is 40 kilograms, and we want to ensure that this whole system is in static equilibrium. So let's go ahead and draw the system together. And again, this is part of the given information. So we're going to have some kind of connection here, and we're going to have a horizontal rope like so. And then this leftmost support is support D. And then this ring here is E. Now from E, we're going to have a cylinder hanging vertically here. And this is cylinder A. Okay, this is cylinder A that we eventually want to get the mass of. Now coming off of E at a 30-degree angle, we have another rope that is actually going to wrap around a pulley. So here we're going to have a pulley, and this is going to be pulley B. And, this pulley is going to have some kind of attachment here that we're not, that too concerned about. But around the pulley, hanging from the pulley, we have another cylinder here that is cylinder C, and the mass of cylinder C is 40 kilograms. So again, kind of looking at this, this is not, the most beautiful artwork, but we have a cylinder C that has a mass of 40 kilograms, and it is attached to a rope that's wrapped around a pulley, okay? And this rope, after it's been wrapped around the pulley, is attached to a ring at E. And then at E, we also have another rope, ED, that's attached to something off to the left, and a cylinder A hanging here, and A, the mass of A is what we want. Okay, so let's think critically about this and see how we go about solving this. Well, if you remember, pulleys support a constant tensile force throughout their length, okay? Which means that whatever force is developed in this segment of the pulley, it's going to be that same constant force all the way through to this point, okay? So the first thing we need to do is get the weight of the cylinder at C, and that's going to be the mass of C times acceleration due to gravity. So we're going to have 40 kilograms times 9.81 meters per second squared. So we get 392.4 newtons. Remember, a kilogram times meter per second squared is a newton. So that's definitely a force that is going to be exerted right here. But remember, it's going to be the same constant force as we wrap around to the other side of this pulley, okay? So here's how we can kind of draw this out a little bit more definitively. We have the weight of C is 392.4 newtons, and this C has wrapped around a pulley that is right here and is attached to the ring at E. And here's our 30-degree angle. And then we have here a force in DE. And then we have the weight of A hanging here, okay? So this is kind of our free body diagram of the entire system, all right? So again, because pulleys exert a constant tensile force throughout their entire length, we can further simplify this as the following free body diagram. 392.4 newtons at 30 degrees. We have the weight of A that we don't know. And then FDE, we also don't know. So looking at this, now this free body diagram seems like a very familiar diagram. So here we can apply our two particle equilibrium equations for two-dimensional systems. We're going to say sum of the forces in the x direction equals 0. And when we sum forces in the x direction, we're going to have minus FDE, and then we're going to have plus 392.4 newtons times the cosine of 30 degrees. Let me write this somewhere else because I'm running out of room. Sum of the forces in the x direction equals 0. And try this again. Minus FDE plus 392.4 newtons times the cosine of 30 degrees equals 0. That's everything with an x component. So do a little bit of rearranging. We can get FDE as 392.4 times cosine of 30 degrees, and I get 340 newtons as FDE. And then we can sum forces in the y direction equals 0. And here we're going to have minus the weight at A, and then we're going to have plus 392.4 newtons times the sine of 30 degrees equals 0. So doing a little bit of rearranging, we get the weight at A as 392.4 times sine of 30, which is just 1/2. So we get 196.2 newtons as the weight at A. Now, if you stop here, you're not quite done yet. You're technically going to be incorrect because notice that the problem statement said, what is the mass of cylinder? What is the mass of cylinder A, right? This is the weight of cylinder A. So to get mass, we're going to say, remember, weight is equal to mg, all right? And so if we want mass, the mass of cylinder A is going to be the weight of A divided by acceleration due to gravity. So 196.2 newtons divided by 9.81 meters per second squared. So the mass at A is equal to 20